Okay, welcome back. We're going to start this third session with a series of short talks. I've been asked to chair these. So first speaker is Maja Jablonska from Australia, and she's going to talk about stellar spectra. Yeah. So the mic is there, and then you have here So you have 5 minutes. Yes. I will let you 1 minute warning.
Yeah. Yes, thank you so much. Hello, thank you so much. I am Maja. I am doing my PhD at the Australian National University, and I am very happy to present some of my things that I'm doing at the PhD currently. And what I'm aiming to do is to provide some framework for computationally efficient synthesis of spectra for stars with some stuff going on, such as spots or pulsations. The motivation is that we are going to have more and more data. Maybe we are not in the regime of overwhelming amount of spectral time series yet, but first of all, from spectral time series, you can get synthetic photometry, and sometimes these effects are seen in photometry as well. And second of all, well, this data will probably come at some point, so it's good to be ready. Applications are just the examples. I'm also thinking of microlensing. I really like microlensing, like every Polish person, I believe. And now I will walk you through the workflow of my software. So I am representing every star as a mesh, and it's just like in a computer game. I'm just tessellating the star, and to each of these little triangles, I have a separate vector of some parameters, such as temperature, surface gravity, abundances, that depends on the needs of the user. And all of these triangles have a synthetic spectrum generated. So we have a lot of singular synthetic spectra for each of the triangle. Then we can Doppler shift them by the element's radial velocity, and then we multiply by the element's projected area. Sometimes we have some occlusions going on in binaries, and sum it up, and all of that is written in JAX, which is differentiable, and it's a forward model that should be fast and runnable on GPU, and differentiable with respect to any parameters we give. The backbone of the spectrum emulation part is work led by Tomasz Różański, who is a postdoc at ANU, and this is a transformer-based spectrum emulator. Please try it out, it's publicly available. And I will now just demonstrate a few examples. So you can do star spots. Just a note, I am actually not really resolving any physics. I am just studying the link between the surface inhomogeneity and the resulting spectra or synthetic photometry. So I am assuming that this star spot configuration has been calculated somewhere else, and therefore we can modify anything we want. So you need to be a bit careful not to provide any absurd star spots, but who knows it's really happening in stars. I decided to keep it as flexible as possible. And here are just some examples. This is a bit of an outrageous example of just ion changing without the temperature change. It's not really realistic, but I really wanted to see the changes in this particular ion lines. You can see that some of them are changing pretty drastically. And this is what I wanted to test for. Of course, we need some more realistic examples as well. This is an animation showing that as the star rotates, we see these lines appearing and disappearing, which is what we would expect. Again, we can do pulsations. Cepheids might not be the luckiest example because they have puffy atmospheres, and it's not really easy to represent with such a stellar mesh, but they're also simple, so this is what I have chosen for this animation. In reality, I think that some more solar-like stars would be much more robust, but nevertheless, we can see the light curve resembling a cepheid, so that is something that made me very happy. And eclipsing binaries, where I am resolving the occlusion as well. And you can see, you can easily produce the stacked spectra where you can see the lines shifting and disappearing, and then produce a synthetic light curve as well. And what I really wanted to do is to make it easy to stack these effects on top of each other. So you can have binaries that are spotted or pulsating, and then microlens it, which is not added yet, but I really want to do it. So that's my goal, to make it easy and, again, hopefully computationally fast. And differentiable. So JAX provides automatic differentiability with respect to any parameters. So you can, I hope this will pave the way to some nice inference techniques based on gradients. So here's a gradient in respect to input ion abundance. And here is the performance. It basically scales linearly with wavelengths, but it also depends on the mesh. This is all published on GitHub. Paper is in preparation, but you can already install it. It's a Python package. And I think that could be a nice collaborative effort. So if you are interested in anything star-related, please feel free to reach out. That would make me very, very happy. And thank you so, so much for your attention.
Thank you, Maja. Time for a quick question. Yeah, Josh.
As you increase the number of meshes, it looks like you were saying you're getting a linear in time of how long it takes to calculate. But the meshes become more and more kind of correlated with each other. Is there a way to exploit the fact that adjacent meshes are going to basically be almost identical to each other?
Oh, that is true. So I'm not really optimizing for that at the moment. I am just, again, calculating the same thing for all meshes. What I would like to do in the future is to make some sort of an adaptive mesh, because, for example, for a fast rotator, we really don't need to have a super fine-grained mesh in the polar regions. So that's something that's not done yet, but I'm thinking about it to optimize. Thank you.
Thank you, Maja.
Thank you. Thank you so much.
Next speaker is Peter. I don't have the title, so you're going to talk about outliers in spectroscopy?
That's the plan.
Yeah, go ahead.
Okay, there we go. All right. Hello, everyone. I'm going to talk about galaxy spectroscopy, not stellar spectroscopy, and on outlier detection that we have, actually some kind of follow-up work which we've built on the latent space of this model. So hang on, there we go. So if you want to represent galaxy spectra, you have to contend with two fundamental degrees of freedom. One is the redshift, moving everything, basically technically stretching everything out towards the red for the cosmological expansion. And then there is a change of the spectral type, if you will. And so you can see both of these changes playing out. The rest frame spectrum on the left-hand side moves from something that's quiescent to something that is highly star-forming. Where if you were to use, say, an ordinary architecture that is not things like a fully connected or convolutional network, then the fact that there are these shifts that occur because of the redshift means the representation is not actually particularly condensed or effective. So what we've built is a model that uses these 2 degrees of freedom. So you can read this, if you're a statistician, you can read this as a probabilistic model where you have kind of 2 degrees of freedom, the redshift and the spectral type. And we are representing the rest frame model of galaxies. So at redshift 0, we are going to represent that by a decoder. And then we're going to shift this and apply any sort of resampling operation to make the model look like the observed data. To complete the picture, we obviously have an encoder at the front end, so that's now an autoencoder. And that means that this autoencoder is now challenged, or it's tasked, to find the rest frame features given the observed frame, which means that including the shift. So there's an attentive element in here which can be used in order to have a translational invariance. So if we apply this, what we get is a very low-dimensional representation of spectra. These are spectra from Sloan. We have also done that with DESI. And what you can see here is this is a compression. It goes from something like 5,000 spectral elements down to 5 to 10 numbers. So the representation, the model that you see here is 6 numbers. That means that the underlying problem is much, much lower dimensional. If we were to exclude active galaxies, we could do it easily with 2 dimensions. It's fine. So there are cases in which you need a higher dimension, specifically around that region here. This complex is where you see line broadening and absorption or emission, and representing that is complicated. or at least more complicated. So, since I'm at Stanford, I have to ask the question, is this a foundation model? And it was never conceived as one, but I'll show you an example of kind of how we kind of base this representation that we have and make predictions that we never intended to make with it. Right, so let's move on. The latent space that we get here is shown in a UMAP. The thing that is so important about these architectures is that you can compress all of the information down into a small set of numbers, and those mean physically something. So you can see the ordering as a function of redshift or stellar mass or other properties as star formation rate very clearly being evident in the latent space, and that is useful. Since this is a session on outlier detection, what are we doing for that? We are using a normalizing flow, something that I think Ben mentioned earlier, how we could use this. We're using a normalizing flow in the latent space in order to represent the probability of a certain instance. And that means that we can now ask the question, which of the objects are very, very unlikely compared to the training data? That removes the ambiguity of how we define it. It's defined by the latent space. If it's in a part of the latent space that is rare, it's going to be called an anomaly. So what are these anomalies? Here's an example where we did this with DESI, the early data release of DESI, and you can see the top anomalies up here. The number 2, the second row here, is just a star. It's a glitch in the data processing pipeline early on that had stars in the galaxy pipeline. Even after the spectrum was taken, the pipeline thought this is a galaxy. It is not. It's a beautiful star. But you find also more interesting things like the lowest one, which is a broad absorption line quasar. Only a handful of these have been discovered. We didn't search for these. This was completely unsupervised. This is just rare. And it works totally fine. I should say that we find very, very few artifacts that come from the instrument itself, because the data quality is actually quite good, even for this early data release, and because of the robustness that we have built into the architecture with the attentive elements in the encoder. Let me move on. There's a follow-up work. Another question that arises with outliers is the specific question, what makes this an outlier? And so we've built this paper, I pointed this, to this paper by Jeff Shen, where we used an occlusion method. Basically, we took a piece of the outlier spectrum and put it into a baseline spectrum. And if our probability for the outlier score, so the log probability for the normalizing flow, decreases, that feature was apparently very important to be labeled as an outlier. So we can automate the search for these outlier features. And then lastly, here's very new work of using the same latent space in order to make predictions on the infrared emission of galaxies. That shouldn't work because the infrared emission is driven by AGNs or dust, and the relation to the optical is very tenuous, but it works really fine. An SPS model cannot do this, but an empirical model that we've trained on the right-hand side matches the WISE data just fine down to the noise level. We have no problem in making that prediction, but SPS models have that problem. So we asked with feature attribution the question, which of the things have we exploited? What aspect in the spectrum have we exploited in order to make that prediction? And you can see there's a bunch of lines that appear, and there are kind of weird lines in there, such as strontium 2, which is related to AGB stars. So it's a certain type of stars. They're important in the production of dust, and therefore they're important to make the relation to the infrared. And this is an example of using these heavily compressive architectures to find a representation that is very meaningful. And that means that what we can do with these architectures is find actual new physical insight out of a kind of a ton of data that we couldn't easily compress. That's one of the things that I like a lot about this field right now, and the capability we have both with a lot of data and with very purposefully designed architectures in order to find meaningful new things. And I'll end here. Yeah, so I like to kind of not manipulate the data, I like to manipulate the model, and that's what we are doing. I don't want to shift anything if it's noisy or if it's artifacts in it. I would like to represent, basically I'm a statistician, which means I write down what the fundamental problems is, I write down the forward model, and kind of that's what we do here. And all of the garbage, all of the sort of the junk that exists there is sort of added on top of it. It's sort of the representation of the data. But I would try to model the sky or the galaxies out there, not the data itself. And so this link in between, this resampling operation, is actually quite important. On the other hand, using the observed frame is useful if you want to have sort of an explicit reasoning of, say, the redshift variation, right? If the redshift variation is very strong and very quick, then what we are doing with a redshift independent representation is not useful. But if you believe that galaxies actually are the same over reasonably wide redshift range, then compressing everything down into a rest frame model, regardless of what the redshift is useful.
I think we should move on. Sorry, but you can catch up with Peter later. Thank you again. Next speaker, Charlotte Ward, talking about transients. Thank you.
Hi everyone, I'm Charlotte. I'm a postdoc in the Astro Data Lab, and I'm just planning to talk a little bit about multi-resolution joint analysis techniques that will help us to make the most of Rubin and complementary data from other surveys for both galaxy science and time domain science. All right, Okay. So the context for this work is that Rubin will be providing us with great time-resolved and very deep data, but we can push this even further by jointly analyzing data from Rubin with complementary surveys. And I think of these in two categories. The first is we have high-resolution space-based imaging from Euclid, Roman soon, JWST, which helps us push the wavelength coverage into the infrared. It helps us to deblend systems that are hard to deblend in ground-based imaging. And on the other hand, from the time domain point of view, we also have other surveys in the south, like LS4 and HADPI, which will provide us with even higher cadence, but very low resolution imaging. And this can help us to study transients by combining all of these surveys together. So this has motivated the development of Scarlet 2, and this has been the work of Peter, Benjamin, Matt Sampson, and others in the group. And this is an extension of Scarlet 1, which is the main LSST pipeline deblender, but it's written in JAX so that we can run it on GPUs, and uses neural network priors on galaxy morphologies to help stabilize deblending. So this is within a class of models, model approaches, where we have a model for the sources in an image. We know what the galaxy positions, SEDs, morphologies are, point source positions. But we also have a model for the observation. We know what the point spread function is. We know what the WCS is, the depth, and whatnot. So we can model all of the multi-resolution data simultaneously by rendering our source models to look like each observation, calculating likelihoods and fitting all of the data that we have. So this code has been built to be flexible for a range of science cases. We're hoping to use it for the joint analysis of Euclid and Rubin imaging, where a large fraction of Rubin galaxies are overlapping other galaxies in ground-based imaging, but with Euclid and eventually Roman, we can use that high resolution to help to deblend the galaxies. But we can also use it to create multi-survey light curves from these various time domain surveys. So to summarize situations where this might be useful, if you have a particular transient and you'd like to combine the data across all of the surveys without worrying about whether you have a reference image that doesn't have a transient, without worrying about whether your reference image is a mismatch between surveys, you might have an AGN which is already there. So we can use this to create multi-survey light curves while simultaneously modeling the background galaxies and the host galaxies. And we can get well-sampled posteriors on the various parameters of interest. So just to show some examples where we hope for this to be useful, one use case is looking at the gravitationally lensed supernovae that Rubin will detect. So Rubin is predicted to find sort of 50 to 100 gravitationally lensed supernovae per year, which will be useful for measuring the Hubble constant. But the majority of these will be marginally resolved in Rubin imaging. So in this plot on the right, we can see LS4, which is a lower resolution, high cadence survey at the top, where the system is completely unresolved. In the middle, we can see the marginally resolved Rubin imaging of the system. And at the bottom, we can see its space-based resolutions. We can see the individual multiply imaged supernova, as well as the host and the lens. So this framework allows us to model all of this data simultaneously and extract the photometry from these blended systems to help with our time delay cosmography. Another application we hope this to be useful for is for AGN host decomposition. So we're interested in looking at very high redshift compact galaxies hosting AGN, where we need to decompose the SEDs of the host and the galaxies. And this is something that we can use to help us identify low mass AGN and AGN out to high redshift. We're also interested in the search for wandering massive black holes with Rubin and other complementary surveys. So there are a couple of cases where this can be useful. So one example is looking for AGN, which are spatially offset from their host galaxies. And we can use these methods to identify a variable AGN that is offset from its host in time domain imaging. On the right, I have a plot of one of these such objects found by Annavi Uppel, who is also here. And she found this with a different technique, astrometric jitter, where you look for difference in the position as your AGN becomes higher and lower in flux. And then we were able to use Scarlet to model and decompose the system to get good host AGN offsets. Another example is shown on the right here. So this is the first tidal disruption event that was offset from its host nucleus identified in an optical survey. And in this case, this was so these are usually nuclear transients. A supermassive black hole at the center of a galaxy swallows a star and produces a flare. But in this case, the ZTF imaging suggested there was a 1 arcsecond offset from the host nucleus corresponding to about a kiloparsec. And that's the ZTF imaging is shown in the top. We were able to confirm this offset with Scarlet 2, and then motivate higher resolution HST follow-up, as well as Chandra and VLA, to show that this was a tidal disruption event from a 10 to the 6 solar mass black hole wandering on the outskirts of a galaxy that hosted another 10 to the 8 solar mass black hole. And we're hoping to find many more of these in Rubin. So I will leave out my summary. We're hoping that this framework to jointly analyze data from space-based and ground-based surveys will be helpful to help us maximize what we can do with Rubin. And if you have any questions or possible applications of the code, we'd love to chat more, and our documentation is now available. Thanks.
A question there.
Do the light curve error bars still remain Gaussian, or are you able to produce some sort of marginalized view of every time series point that takes into account, the full posterior of all the stuff underlying?
Exactly. So we have a sampler, so the flux of each epoch is a free parameter, and you can just get the full posterior over those parameters.
How kind of long-tailed is the photometry in some of these kind of cases?
You mean like what do the posteriors look like?
Yeah, of an individual photometry point in like a complex system, is it possible it's 10 times fainter?
That's a good question. So I've only looked at relatively simple systems in ZTF where the posteriors are Gaussian, but it would be interesting to look at them in complex blended hosts, and we can certainly do that. That would be useful. Yeah.
Well, I think, we should move on. Thank you. Next speaker, Linnea Wolniewicz. She's going to talk about probabilistic detection of anomalies in stellar light curves. Yeah, you move forward like that, and the pointer is just there. Give you a minute warning.
Hi, so I'm Linnea Wolniewicz, and I'll be talking today about our work titled Dipper Detector, Probabilistic Detection of Anomalous Dimming in Stellar Light Curves. So the goal of this work on a broad scale is to detect anomalies in stellar light curves, where a light curve is just defined as a star's brightness plotted over time. But specifically, we're actually interested in detecting anomalies in light curves with very complex behavior. And in this case, we define an anomaly as a change in this behavior, such as what I've injected here in the red rectangle. And in particular, the anomalies we're interested in are dimming events that occur in young stars. And these events are poorly understood. There's a variety of things that they can be. These 4 examples here in red circles are exocomets, but they could also be protoplanetary disks, occulting a star, or some exploding planetesimal, to name a few options. And the goal of this work is to check these anomalies probabilistically using a generative model without assuming any physical parameters of the anomalies themselves. And the probabilistic generative model that we use in this work are Gaussian processes with a quasi-periodic kernel. And if you're not familiar, a quasi-periodic kernel is a radial basis function multiplied by a periodic kernel. And the radial basis function allows us to incorporate correlations between adjacent time points. And the periodic kernel allows us to incorporate the strong periodic signal that we see in these light curves, such as the one you see on the right here. So on the left, we see this quasi-periodic function plotted over time. On the right is that light curve we were looking at before, but now it's colored by the covariance matrix of this quasi-periodic Gaussian process. And we want to use these Gaussian processes to identify which intervals are anomalous, such as this red one, and which are not anomalous. And how we do this is we hold out intervals during Gaussian process fitting, and then we evaluate the p-value of that interval under the learned multivariate normal distribution. And we can do this exhaustively by just brute forcing, searching every possible interval in the light curve and determining its p-value to find the anomalies. But that's very computationally expensive, so we also propose a greedy alternative that instead grows anomalous intervals out of highly residual observations. And we can look at the performance of this greedy approach in practice. So here I've injected an anomaly in this complex light curve. It's in red, and you can see that the Gaussian process greedy approach correctly identifies the anomaly. This is because it's a very short period. So when we look at the residual plot on the right of the Gaussian process fit with observations, this anomaly shows up very clearly. And so the greedy approach can catch it. But the greedy approach fails on very long period anomalies, which we can see is anomalous by our eyes, this large dip. But because the Gaussian process is able to fit to this anomaly, it is not identified as anomalous by the greedy approach because there are no residuals. But this is where the exhaustive approach is very effective. Although it is more expensive, when it iterates over the interval that contains the anomaly, holds it out and evaluates its p-value under the learned multivariate normal on the rest of the light curve, it has a very low p-value. And so it detects the long period anomaly. And we can summarize the results of both of these approaches by injecting anomalies in the light curve you see here on the left. And we can inject anomalies of different widths, this is the x-axis, and different heights or depths, and this is the y-axis. And we see that on average, in the red square, which are depths greater than 1 standard deviation and widths less than a day, both methods are achieving over 90% recall of these injected anomalies. And while these Gaussian processes are very performant, they're computationally expensive. You have to refit them to each light curve. So in future, we're interested in replacing these Gaussian processes with a generative neural network. And we can additionally use data sampled from our fitted Gaussian processes and define a distribution over those parameters of different light curves to generate training data to train a very data-hungry method like a neural network. That brings me to the end of my talk. Feel free to come and chat with me.
Thank you. Any question? Short? Yeah. Right.
When you say exhaustive, are you talking about literally brute force exhaustive or something like dynamic programming that lets you effectively do an exhaustive search?
Yeah, very good question. In this case, we're doing an approximation of an exhaustive approach without using dynamic programming because we're just doing, like instead of evaluating every possible interval, we slide, say, 10 steps instead of every step and then evaluate the performance. But we're interested in looking into dynamic programming for this. That's,
I think dynamic programming might be really useful here.
All right. Thank you again. Move to the last speaker of this session, Christine Ye. She's going to talk about AI agents now. So this is, you move forward like this, and this is the point.
Thank you. Okay. Hi, everyone. I'm Christine. I'm an undergrad at Stanford, and this talk is not quite about anomaly detection, but I hope it's useful and interesting regardless. So I assume some people, at least some fraction of people in the room, like to use language models as part of their day-to-day research flows, or maybe their students do, maybe for answering questions or writing code. But probably you've all wondered which of your research tasks can current AI models actually reliably and rigorously do? Which ones can I trust it to do for long horizons without having to go, babysit every task it takes? There are lots of common benchmarks in the language model literature that will test for things that are kind of adjacent to this, things like scientific reasoning or mathematical reasoning or general agent abilities like coding. But there's not really benchmarks in the literature, at least not for language models, that simultaneously measure all the things you would need to do to actually maybe want to trust a language model to do a large research task for you. Things like long horizon execution, the ability to follow your instructions to the T, and to exhibit high-level scientific understanding throughout all of that. And so our solution, and this is a project of this center, is Research Bench, which is a new benchmark. What we've done is we've taken 22 peer-reviewed astrophysics papers and worked with the authors to decompose them into 120 expert-written subtasks. Those subtasks represent the core contributions of the paper, and so in order to pass the benchmark and get scores on the tasks, the agents are required to replicate the methodology and the core findings given just the manuscript, the data, and an execution environment. And then because we've written the tasks in an objective way, we can then evaluate the end results automatically. I want to emphasize that these 22 papers are just the start. We're hoping both to work with the community to expand, and also we have several other expansion efforts underway. So here's a sketch of the actual workflow. We start with a full manuscript of the research paper. We also have the specs on the data set, and then we have the execution requirements. We work with the authors to generate objective tasks that capture the core contributions of the paper and generally the core methodology that would be required to implement, tested against some numerical output that is known. Simultaneously, we place the language model in a code execution environment, and that code execution environment has access to things like a GPU, bash execution, code execution, and also the manuscript of the paper and the data. And from that, we allow it to run autonomously for anywhere from 10 minutes to 6 hours. That produces a whole trace of all the language model's actions, including all of its thoughts, the code, and the actual outputs, and that all gets graded both automatically, and then in our experiment, we also worked with the authors to do human evaluations. Just as a quick example to give you some concrete, look at what the task looks like. This is one of the hardest tasks in the data set. This is from the Abacus paper. It basically requires implementing the full Abacus force method. This is obviously very difficult for a language model, and so it really doesn't make very much progress on it, but at least if you look at the trace here on your right, you can see that it's able to do some attempt at writing a sketch of the code, even if it's not able to implement it to a T. And so the conclusion here is that at least on Research Bench, which I'll emphasize is like a pretty ambitious thing to ask a current language model to do, frontier models struggle a lot. Even the strongest model gets like 20%. And especially on the most difficult tasks, you can see here, the success drops off dramatically. I'll say that like the language models, even though they demonstrate fairly poor numerical performance. In our human evaluations, there's a more rich story here. We had the authors rate the traces from the best scoring papers and grade them on the intent interpretation, the quality of execution, and the amount of hacking or erratic behavior. And so many of them rated the traces actually showing quite sophisticated reasoning and intent, but just small logical failures and small execution weaknesses in the agentic environment that made the actual full trace perform poorly. And so among the failures, there's only a small fraction of failures are really catastrophic, as in the agent completely misunderstood the task or like strong technical execution. The rest are partial failures with small logical missteps or small issues with the execution. And so I'll just conclude quickly to say that Research Bench, we believe, is the first benchmark in astrophysics, and I think in science more generally, for paper-level scientific research capabilities. Again, asking for paper reproduction is quite ambitious, but I think it's good to set our goalposts and have the community input here while we're still relatively early in the process of using language models in research. And I think the work we've already done so far has revealed a lot of interesting new insights into how frontier language models perform on real research tasks. We are seeking as much community input and contributions as people are willing to work with us on. I've listed the GitHub here if you want to look at evaluation traces or if you want to look at example tasks, and the GitHub is actually also how we accept contributions. But if you're interested in providing feedback or contributing, we'd also love if you could get in contact via this form so we can work with you more directly. And yeah, happy to take any questions about the work.
And can the poster speakers for the first session come and line up here, please? And okay, let's go.
Great talk, thank you. Is there, have you seen your kind of agents start to cheat? So basically one agent saying, this paper has been reproduced, at which point that was the only sort of, basically that sentence would have been the entire validation. So finding shortcuts that you didn't intend to.
Yes, so one concern we had that we actually dealt with a lot was basically the reproduction values are values from the paper. And so no matter what you do, if you give it the paper with the values in it, if it works for an hour and doesn't figure out the answer, no matter how hard you prompt it, it will tend to just copy those values over. And so to work around that, we had to actually go through and mask out all the relevant values. But of course, that doesn't stop it from, let's say, trying to guess answers from the pre-training set. So it's still sort of an imperfect thing.
Okay, let's thank Christine again, and let's thank all of our short speakers.